Okay, do you see the movie? So what is your, okay, let's just watch and develop. And I was starting the interview several times from Adam. Let's start from this. What do you think about this movie?
Just different orbitals.
Okay, so any observations, anything you didn't expect?
I don't think so. Maybe there's more than I remember there being more
But okay,
patterns.
is there a progression as we go from bottom to top in the number of
Looks
orbitals?
like
Lowest orbitals?
so just add 2.
No, the lowest
sorry.
is 1, right?
Yeah, 1, 2.
1, 3.
Yeah.
1, 3, 5, 7, right?
Okay.
Thank you. Wyatt, do you have any observations that Nate didn't mention?
Every level or every time it increases like 1, 3, 5 like that, but it also there's like a different plane of movement.
Okay.
Like the bottom 2 just spin like this way, but then the ones higher up will have like an angle of spin.
Okay. What about speed of rotation, speed of spinning?
The higher ones spin faster.
Do all higher up spin faster, or there is a gradual change of how they spin?
Gradual, depending on
How far from the center?
the ones further from the center spin faster.
Okay, yeah. Thank you much. So Adam, what I would ask, what do you guess my question will be to you?
What do I think of it?
Okay. And what do you think, or what specifically you would like to ask yourself or myself?
It looks like just SPDF orbitals.
And next letter is G.
Yeah, G.
Okay. But typically they are drawn as something static, right?
Yes.
Here,
They are. They have motion, they have rotation,
okay. So some
momentum.
people tell that it is like flowers with petals, right? So how does rate of spinning depends on number of petals?
Oh, I'd suppose the more petals, the faster the rotation.
Excellent. Thank you. Sybil, I apologize. All questions are completed by guys in the back row. So basically, the goal of today's meeting is to confirm the wording by Adam. So larger number of petals spin quicker, and whatever we see here is really great, but if you would provide math behind this rotating images, it will be too much. It's doable. You already have enough mathematical background, but then we need at least 1 month or a couple of weeks more. So I'll just skim through most important things that if ever in your career you need to dig deeper, you'll be ready to go through. So in previous image, it was 3-dimensional, right? Here it is 2-dimensional, right? And it looks like d orbital. So to my understanding, it is the project that Nate is not Nate, Joe is currently doing. Joe, is it right?
Yeah.
Okay, so it is a little simplification compared to real life. Instead of 3-dimensional, it is 2 because we have limited numerical opportunities. But it has 4 petals and it rotates with certain speed. Another thing that I may have asked to Sybil, but typically when we see these images in like freshman chemistry, they're static, they're not moving. And now we are, well, it's already told, we are focusing on the moving, and it is intrinsic, it is their property. If one adds together two counter-rotating in opposite directions, then it will be static. And then it is what used as dx square minus y square and so forth. But actual solutions of Schrödinger equations, they are moving. So eigenstates of angular momentum. Yeah, here is your thing, and I'll take it creatively. Some of you do not change initial temperature and momentum. Some of you change other parameters, but general pattern is applicable. So last time we started working on either rigid rotor of diatomic molecule or electron around the nuclei. With angle, it accumulates arc length. And if we set up wave function depending on distance from center and angle in polar coordinates, and we want to explore how wave function is changing in respect to the arc length, we practice this. Is it possible to use chain rule, or it is different word? Differentiation of complicated, complex, not complex, of change variables. Okay, differentiation by change of variables. And if we temporarily assume that radius is not changing, then it will be derivative over arc length will be same as derivative over angle, but divided by this metric tensor element if you plan to go into special theory of relativity. So the angular momentum is defined as a cross product of momentum and distance from center. And if we compose it and plug in our derivative over arc length, and we use it because we cannot use linear, the direction is always changing, so we need this derivative over arc length. Then radius cancels, and we get the angular momentum as a just Planck constant imaginary derivative over angle. This is a main key towards any rotational motion. It is labeled LZ because it is for motion in XY plane, and it is oriented in Z direction. So if you want to compose the Hamiltonian, there is no potential energy right now. There is only kinetic. And kinetic energy is momentum squared over two masses, right? We multiply up and numerator, denominator by radius squared. And then we can identify that radius times momentum will be our angular momentum, right? You didn't quote me line yet. And denominator, instead of mass, it has mass times radius from center. So mass is measure of inertia. Mass times distance from square is momentum of inertia, or just measure of inertia. It's often called as with uppercase letter I, so LZ squared over 2I. This is our Hamiltonian, right? And at least today, maybe a little bit longer, we will play with this Hamiltonian. Of course, and opening the brackets, so second derivative over angle. Very similar to what we had for like one-dimensional motion. And our goal is to set up wave function which depends only on this variable and find eigenstates of Hamiltonian operator. At least it is our natural direction of thought, right? Find eigenstates of Hamiltonian. But we always look for shortcuts. So due to your knowledge about the Heisenberg equation of motion, we know that if an operator commutes with Hamiltonian, then it doesn't change over time. And there is another aspect. If the same theorem can be converted logically in the following statement. If an operator commutes with Hamiltonian, then they share the same set of eigenvalues. Make sense? It was yes, no, more or less. My brain was, when I was in undergraduate studies, was rejecting this statement. I didn't like it, but it is based on this. So if Hamiltonian, if energy doesn't change over time, due to this equation, another variable also doesn't change over time, therefore their states are shared. Now, our Hamiltonian is based on LZ squared, right? An operator commutes to any power of itself, right? So LZ commutes with LZ squared. Now, LZ squared commutes with Hamiltonian, and LZ also commutes with Hamiltonian. So if I didn't make any errors in this logical stream, then by finding eigenvalues of LZ operator, we will immediately learn eigenvalues of Hamiltonian operator because they share the same set of eigenvalues. In the past, we did a similar thing for the free space. We found eigenvalues of momentum operator. Then maybe I didn't declare it, but since Hamiltonian and momentum did have the same eigenvalues, we just plugged eigenstates. We plugged eigenvalues of momentum into Hamiltonian and found the dispersion, found the spectrum of states. So we are going to practice the same ideology. So let's just find eigenvalue problem for the angular momentum LZ operator. So operator, unknown function, eigenvalue, unknown function. And just for comfort, we can divide left and right by h bar. What is the dimension of Planck's constant? I think I'm making maybe unnecessary stop, but what is your opinion about dimension of Planck's constant? Sibyl, I'm going to approach you while I'm walking. You can think. In the plane wave, we had e to the power IR, IRP, momentum times. On the other hand, power of exponential in this Bohr or whatever, Louis de Broglie is action. So action, R times P, angular momentum. So
repeat the question, sorry.
So what is the dimension of Planck constant?
So that's what I'm trying to.
So let's think together. There are two answers, and they both are correct. Typically, when we do evolution operator, we have e to the power I h bar t time divided by Planck constant, and power of exponential must be dimensionless. So h times t, energy times time, and Planck constant are of the same dimension. Would you agree? So what's the dimension of Planck constant?
Energy times the
Time.
time.
Okay, good. And thank you, Sibyl. And when we did, I'm making second circle, when we studied plane waves, right? We also had this position times momentum divided by Planck constant in the power of exponential. Do you remember it? Okay, But if you accept it as my word, and we accept that power of exponential must be dimensionless, what is other way to say dimension of Planck constant is?
Position times momentum.
Excellent. Thank you. Thank you. And if we play, just the writing facility doesn't work here, so I need to relay what is shown here. So Planck constant is either energy times time, or position times momentum, or just angular momentum, because position times momentum is actually what is angular momentum. In fact, the Planck constant itself was designed to match this stuff. So and based on this dimensionality, if you divide LZ over h bar, it will be dimensionless thing. So angular momentum increases in fractions or multiples of h bar. Okay. Now we can call it as letter M. And if you were not yet bored in freshman chemistry, you may remember for hydrogen atom 4 quantum numbers: principal, orbital, magnetic, and spin, right? Letter M would be matching which of them? Magnetic, yeah, thank you, Sybil. So magnetic quantum number. So by solving eigenvalue problem for angular momentum, we'll find wave function as function of azimuthal angle, and we find magnetic quantum number. Okay. So in this morning email, again, I probably mixed general and particular solutions, but now I can correct my error. So first we find general and then particular, right? So it's again this probably the simplest differential equation. Derivative of the function of independent variable equals to the unknown function, right? So if you divide left and right by function and multiply left and right by increment of the independent variable, we can integrate left and right parts, right? And then on the left, we'll have integral of 1 over function as logarithm. On the right, integral of like constant will be independent variable, correct? And then if you place left and right parts into the power of exponential, we get that e to the logarithm of psi, which is psi, equals EIM phi, right? Quite similar to what we had for plane wave. For plane wave, here it was momentum, here it was position. Now instead we have angular momentum, dimensionless angular momentum, and angle. So angular momentum times angle is also of the dimensions of Planck constant. And to be correct, we also need free constant. Okay, so we do have general solution, and we need particular. So particular solution is obtained by matching. Well, normalization is always needed, but in addition, one needs match either initial condition or boundary condition, right? So here we have two unknowns. We have functional form, but we do not know C and we do not know M. So to find C, we will do normalization. To find M, we will find boundary conditions. And concept of boundary conditions for the rotational motion is not very complicated, but a little away from common sense. You will get through it easily, but just prepare for a little obstacle. And literally, this problem is primary focus for my SSI for her project and complementary background for Joe. The problem that Joe is solving is a little bit more complicated, but it is based on today's derivations. So okay, so normalization. Wave function times itself must be equal 1, right? So conjugated, non-conjugated, this exponential cancels each other, it will be 1. And the function is defined on the area of definition from 0 to 2 pi, right? So we need to just integrate constant from 0 to 2 pi. So it must be equal to the screen is blank here, so I will be writing blind. So here we should have c squared. I'm just correcting what was missed. So c squared times 2 pi must be equal 1, right? And then we solve for c, which will be 1 over square root of 2 pi. So wave function is 1 over square root of 2 pi e I m phi. Value m is unknown yet, but we need to get it by matching to the boundary conditions. So what are the boundaries of the rotational motion? It would be not wrong to say that it has no boundaries, right? It's periodic, but practically, even if you do not believe in boundaries of rotational motion, we need it in mathematical sense because we need to find m. So the wave function is defined on a circle on this like Bohr trajectory, and I don't remember if I was telling the following, but wave function must be continuous. It's typical conditions that everyone requires in calculus, like no discontinuity. The derivatives must be defined in any point, right? Which means like if I have 2 fingers, maybe more, but 2 at least, and I travel across this trajectory, anytime I place 2 fingers on the trajectory and compare 2 values, they shouldn't be much diverging. They should be infinitesimally close, which means if like my first finger is in 2 pi and second is already 2 pi plus little, it means but we are limited by 2 pi. It means after finishing 2 pi, I'm getting to the next circle, which means it will be 0. So wave function at 2 pi and 0 must be the same. Make sense? So this is an analog of periodic boundary condition. And it is literally the same what we did in the MATLAB code when we described plane wave. So it exits one door and immediately enters another one. So basically we already, although we didn't knew it, we already described kind of rotational motion. So wave function at angle phi must be equal wave function at phi plus 2 pi, right? If we plug it into our functional form, em phi plus 2 pi. So e to the power I m phi on the left and right can be cancelled, right? And then we have an equation 1, and then ei 2 pi m. So what are the solutions of this equation? How would you solve it? continuing the turn it, we'll ask quiet. So any solution you can get from the top of your head.
Solving for M.
Yes. Like, what is exponential to the power 0? So if you plug in m equals 0, would it solve this equation?
Yes.
Okay, so White found at least one. Now I'm continuing. While I'm making steps, Adam, you can guess more answers.
Just take the natural log of, I guess, yeah, natural log of 1 over e to the I2 pi would be equal to m, I believe.
Okay, and can you just give example and one more solution? Not by smart formulas, but just intuitively.
Oh, I2 pi m must equal 0.
Well, no, without I, just 2 pi m.
Oh, yeah, 2
equals 0. Or if you have, if it will be I 4 pi, if it makes 2 full revolutions, would it be matching?
yes. Yeah.
So you guess another solution will be m equals m equals 0, m equals 1.
Oh, yeah.
Okay. And then 2 and 3 would work. So integer numbers should work. Do you see it, or you need more words? Yes, yes, yes. Okay, everyone was happy, but I will, since I have slide, I will still give some explanations. So our old buddy Euler tells that exponential, imaginary exponential is cosine plus I sine, right? So it means real and imaginary, and it should be real 1, imaginary 0. So we can independently we can solve together cosine 2 pi m equals 1 or sine 2 pi m equals 0. Is it a better equation? Right. So sine, I'll start with sine. So blue line here, sine 2 pi m, and m our independent variable at this point equals 0. So anytime sine crosses x-axis, it will be solution. So it will get solution in 0, 1/2, 1, 3/2, 2. But let's double check with cosine. Cosine 2 pi m equals 1. So it will be a solution for 0. And the next solution will be for m equals 1. This is not working for cosine, for real part. Then the next one will be for m equals 2, right? So anytime cosines makes cycle and touches line cosine equals 1, it will be a solution. So we do have one equation and infinite number of solutions, right? By the way, if can we expand m to the negative? -1, -2, right? So 0 and any plus any integer number. Okay. So here is the full solution, matching boundary conditions. It's normalized, and this is dimensionless angular momentum, which takes values 0, ±1, ±2. There is the same analogy as with plane wave motion. The imaginary exponential, if you take like only real part, it will show fringes, right? The denser the fringes, the quicker the motion, right? Here it is the same pattern. If the number m is bigger, fringes will be denser across the periodic one period. So this number m tells how quickly our rotational object rotates, right? But we do have traffic signs. So like on our highways, we have like any speed below 80 miles per hour is permitted, or whatever, depends by state. So it's continuous. 80 minus from minus 80 to 80. If it is no, it will be wrong if you do minus 80 from 0 to 80. And here it takes discrete values, same like if it will be like you can either stand still, move forward 10 miles per hour or 20 miles per hour or 30. But if you move in between like 5 or 6 miles per hour, you get a ticket, right? So only discrete values are permitted. Same as if we are all kids getting fun on a carousel, we have only specific speed of rotation. One speed is allowed, another is forbidden, right? So rotation with different velocities. Did they show this image before? At the very, so let's play it once again. Launch it. So the two panels on the left illustrate the solutions for values m equals 2 and m equals 3. The plotting is done in respect to this double line. So when this green line goes beyond this double line, it means real part of the wave function is positive, like cosine. If it gets below, it is negative. And we can have this up and down 2 times for m equals 2, right? This would correspond to d orbital, right? And this is an analog of Bohr's model. So it is allowed only motion on a circle. Distance from center is not changing, and only discrete values of m are allowed. So if you go to the next, to f orbital, it is positive, negative, positive, negative. So 6 nodal points and 6 extrema. In case we take non-integer values, we can solve Schrodinger equation. A policeman will not issue us a ticket for doing it, but it will be not an eigenstate. So eigenstate is the one that is reproduced. We apply Hamiltonian and get the same state. If you use a non-integer number next instant of time, it will change its shape. Like here, it only slowly rotates. Here, it changes its shape. So let's. So you see, it has ugly shape and it changes over time. My CSI, if you're watching, it is very much related to your project. You will do, or you're already doing this one, times magnetic field, which will offset energies based on the magnetic field. Okay. So let's make attempt to connect these things to real life. Here is our dimensionless values of angular momentum. 0, plus minus 1, plus minus 2, and so forth. Since the Hamiltonian and angular momentum operator for this rigid rotator, two-dimensional rigid rotator, since our Hamiltonian is expressed as a second power of this angular momentum, we can simply take eigenvalues of angular momentum, which will be this integer numbers times Planck constant, and plug them into the Hamiltonian, right? So it will be m squared h bar squared over 2 inertia, which means it will be this red circles, red points, which fit a parabola. So rotation forwards and backwards with the same pace has the same energy. Therefore, there will be degeneracy number equals 2. Ground state is 1, degeneracy 1, and all others have degeneracy 2. Yes? So neither myself nor you were lying. We did everything absolutely correct. But this model is simplified in several aspects. So it corresponds to rotation in a plane. But in addition, it is, so it's like two-dimensional rotation. In addition, it doesn't allow, here we are not allowed to change radius. It is fixed. And if we are speaking about diatomic molecules for raw vibrational spectroscopy, we can accept the radius is not changing. But if it is like molecule in a free space, it will make three-dimensional rotations. If we are speaking about like hydrogen atom, even if we do some exotic world, exotic universe where there is only 2 dimensions, the radius will change. If it moves quicker by centripetal and centrifugal force, the radius will will also depend. So our model is like spherical horse in a vacuum. It has limitations, but it is really cool for understanding because it provides, it's absolutely solvable in like a couple of lines. But if we slowly go to a real life, same energy now, and if we make dimensionless, it will be like m squared. If you go to a real life where rotations can happen out of plane, this is a really cool problem that is solvable, but I have a scene of skipping it from the class program just to fit it in place. There, this rotations will be, which have out of plane, will be indexed not by one magnetic quantum number, but with additional angle orbital quantum number, right? And the energy of rotations will be not a square of angular momentum, but it is like provable by solving by total angular momentum by angular momentum plus 1 in the dimensionless things. You can accept it because in previous slides we have m times m squared. Here it will be almost the same, but here you have plus 1. So it's I cannot do anything with it. It's math. If you allow additional rotation in plane and out of plane, it is what happens. And another feature, if we scan through different values of total angular momentum and scan different values of magnetic quantum number, there will be different degeneracy. So for total angular momentum 0, it's non-degenerate. For total angular momentum 1, before we had, it was double degenerate. For rotations out of plane, we get additional states where it doesn't rotate. Magnetic quantum number is 0, but total angular momentum is fixed. If you have total angular momentum 2, we have 2 solutions which correspond, which agree to our simplified solution, and additional 3 states which correspond to a little slower motion in azimuthal plane because it will go out of plane. So degeneracy 5. Next one will be 7. And this already agrees with what you remember from freshman chemistry, what from the first movie at the beginning of the class. So degeneracy is 1, 3, 5, 7. So here I will quickly show some examples of three-dimensional rotations without math, only as examples. So we give up all our math skills from this class and return to the level of freshman chemistry just to visualize a situation with images. So total 4, angular momentum 4, which will be letter like S, P, D, F, G. There are solutions which have absolutely no motion along azimuthal angle, only rotations out of plane. And then as we rotate out of plane by angle theta, we have nodes, lobes, and these nodal planes or surfaces. So plus, minus, plus, minus, plus. If we keep the same angular momentum, but get an increase in magnetic quantum number, it starts, in addition to the structure, it gets nodal plane in this XY plane, right? Plus, minus, plus, minus. If you go keep same angular momentum, but increase magnetic, it gets more along in the plane. And if you go further, it's, you see, it has less motion in the out of plane and more motion in the in plane. So the structure of petals change, right? And if you get to the maximal angular momentum, it has no out of plane motion, and it has this eight petals, like 4 positive, 4 negative in the XY plane. Make sense? So if we look for the images we analyzed, we keep the total angular momentum 4 with degeneracy 8, and we look only positive magnetic quantum number 0, 1, 2, 3, 4. The higher magnetic quantum number, the more lobes and nodes in the plane, as we discussed for our rotational solution. And negative are also allowed. So the higher the total angular momentum, the more is degeneracy and more petals on the edge. If we compare central column, it doesn't move in the angular. If you look for the second, they all have the same pace of rotation. Then here it is double, here is triple, and this is quadruple. So it is basically what you saw in this movie. So if you scroll through, you will see that rotation of the magnetic quantum number 1, it rotates with the same pace. 2 rotates quicker, 3 even quicker, 4 the quickest, right? So if we plug these solutions into equation for transitions between vibrational states, like degeneracy and energy differences, it is a helpful tool towards reproducing the wings in the rotational raw vibrational spectrum. So Joe is doing 2-dimensional rotations. Please do not forget or refresh yourself with equation for cross product. And the definition of angular momentum is cross product of position vector times momentum, and then the LZ component will be determinant of xy, px, py. So the expression for angular momentum, if you give up polar coordinates, will be position times momentum, position along x, momentum along y, minus momentum along y times position along y, x and y. So this operator is needed if we do not want polar coordinates, if you want to describe two-dimensional rotations on a plane. Enough. Thank you for your patience. Thank you for staying a couple of minutes longer. Any questions are very welcome now or by emails, and we'll see you on Monday 2 times. Right? Yeah. Have a nice weekend. Everyone is welcome to disconnect and depart.